Okay, good morning, everybody. My name is Andrew Carnahan. This is lecture 5.2 on peak or polyether-ether ketone. The title of my research paper or study was Mechanical Characterization and Numerical Simulation of Peak Cranial Implants. The scope of this study was to define a computational framework for designing implants with a scaffold-like structure. And the key objectives were to evaluate the mechanical performance of the two different designs and validate their numerical models created. I'll go back to that in a second. So today's cranial implants are typically solid-like and they're made out of titanium. The two designs considered in this study use a periodic scaffold-like structure, as you can see down here. This number down here is the void to volume ratio, and they actually come out looking like this rather than the solid, which is what there is today. And they're made out of, or they're manufactured using SLS, and the possible benefits for these designs is that they could have better osseointegration, which basically means that your body takes them easier and they integrate into your body better. They also would be cheaper than manufacturing titanium, and also better customization to individual needs of patients rather than today's manufacturing processes with the titanium shells. Okay, so the first objective, evaluating mechanical performance. So the researchers created 4 SLS implant samples for each design, and they had the actual cranium manufactured off-site using polyamide reinforced with aluminum particles. That's this up here. It's kind of dark, but they actually secured the samples with the actual surgical screws that they would use in a surgery, just to make it as close to an actual sample as possible. And then they conducted a load displacement test according to ASTM D638, and they recorded the data using a 10mm cylindrical indenter at a rate of 0.1 millimeter per minute. This is where the indentation would actually be the blackest. And of course the test stopped after failure occurred, which ended up always being right around the indenter. So the key results from first objective is that they've displayed that the material behaved linear elastically, as you can see on the load displacement curve. They're able to generate the average maximum bearing load and displacement until fracture for each design with a standard deviation, as you can see in the first table. They're also able to get an average Young's modulus from those results. Also, one of the key takeaways was that design 2 with the void to volume ratio of 0.54 was more optimal compared to the first design because it had a 70% larger load bearing capacity. If you see right there, it's a lot bigger, but they have relatively the same displacement. Alright, so now moving on to the second objective. They wanted to create a numerical model and an analytic solution so that they wouldn't have to mechanically test these designs every time they wanted to make something new or change. So they generated a CAD model using an inverse finite element procedure. You'd have the patient take a CT scan of their brain and get a general idea, I guess. They'd generate a surface from that CT scan, and then they'd insert the different scaffold structures to make their CAD model. Then they actually used ANSYS to solve for the principal stresses and displacements exactly how they had computed for the experimental model. So it was pretty much exactly the same. And they ended up decreasing their mesh element size until the ANSYS solutions varied by less than 1%. And at that point they actually had to mesh to 2.5 million elements and 2 million degrees of freedom. So that that can be pretty computationally intensive. So they actually wanted to simplify it, and they used the asymptotic theory of homogenization to simplify their model, which basically makes use of the periodic structure to I don't know, like basically make it into a shell, and they know that all the principal stresses and displacements will act like the same throughout each structure. And then as you can see, skip forward a little bit. So this was the detailed FE model, which matched the experimental results really well. The tensile strength of peak is 90 megapascals, which is really close. This was the first simplified model, which actually said was like the samples could take a lot more bearing stress than they actually could. So they made a bending correction factor, and it got it back down to a pretty like accurate range. So the detailed FE model and the homogenized model with the bending correction both had a pretty accurate uh, maximum principal stress, and they also matched the maximum displacement before failure pretty well to the experimental results. So in conclusion, again, design 2 they figured out was better than design 1 as far as load bearing capacity, and from the analytical solutions, the results showed that the CAD models are able to reproduce the experimental results, which offers a less computationally intensive alternative to be used in cranial implant design, and it also makes just the whole mechanical experimental process like not as necessary, which is really good. The only thing that I guess they didn't talk about, which they could do more, was this was all like static loading, and if you're actually going to compare these designs to like the titanium samples for today, then you'd need like a dynamic loading case just to see how those compare with each other.